Okay, so I have been asked, as with last week, to kind of walk through the Iowa code and sort of give you, I guess, a tour of the model from the 2022 paper. Let me wake MATLAB up here. What's going on with MATLAB? Maybe I could just close that. There we go. Okay, so first, let's just sort of orient like we did last time. So all the code for today is available on the GitHub site in this Cosavina DFT projects folder. And we're now going to talk about the code in the Spencer Infancy 2022 folder. And as I mentioned last time, we typically partition our code into 3 files. The BAM file, which stands for batch, auto, and multi-core functionality, which is kind of the main experiment file in some ways. And then the sim file, which is the model itself, specified in Cosavina code. And then a GUI or graphical user interface code file, which has got the code to create the graphics to watch the model in action. So let's just first, I'm gonna to do a simple thing, which is just run the model, because typically that's what I do when I'm starting work on a model. I always like to refresh my memory of what the heck is in that model. And the best way for me to do that is to run the model in auto mode with the graphical user interface up and try to figure out what the heck the simulator is doing. So I would then open this run Iowa BAM file. I'd go into MATLAB, and first thing I need to do is go into Cosavina, my Cosavina folder, and type set path to link in Cosavina. And then I'm going to go to the DFT projects Spencer Infancy folder and open up this run Iowa file. And on GitHub, this should be set up in auto mode. That's kind of last time I pushed it to GitHub. That's what I did. And you can always check that where you see this mode line. Just make sure it's set to 1. And that will then run through just a single batch of simulations. So if I then just hit run, it should pop up a simulator, and I'm going to hit pause for a moment. So that's just literally how to launch the Iowa model. Were you guys able to get the model running on your end? Yeah? Okay. Yeah. Fabulous. Great. So let me just orient you to the GUI here, or graphical user interface. The top line is just going to show the visual input. The middle plot is the attention field. So you've got the blue curve is the activation across the attention field. The red curve is the sigmoided output, meaning basically any place where the activation goes above 0 and this is in the dynamic field theory, this concept of only neurons that are above threshold, meaning greater than 0, only those neurons contribute to interactions. So the concept of a peak of activation means I've got a collection or neighborhood of neurons that have gone above threshold and started passing excitation to their neighbors and inhibition to their faraway neighbors. Okay, so you can see this red hotspot here means I've got a collection of neurons around the fovea, which is 0, which have now entered into that peak state, meaning I'm attending to the center of the visual field. So that's the attention layer. Then we've got the saccade motor field down here. That works like just any other field. I should say, actually, both the attention layer and the saccade motor field in this model are what we call selection fields, meaning the neural interactions are such that we have local excitation, we have surround inhibition, and we have global inhibition. And what that means is that there's only ever going to be one peak in the attention field, and there's only going to ever be one peak in the saccade motor field. Okay, and that maps onto our psychological concepts. We always talk about selective attention, so you can only attend to one location in space, and you can only move your eyes to one location in space because your eyes are physical, right? They have to point somewhere. Okay, so these are going to be selective fields, only ever one peak dominating at any moment in time. Now you can see there can be little blips of activation that's above threshold, but only one real hot spot or one peak. So right now you could say this model is attending to the fovea, and there's no plan to move the eyes anywhere in space. And the reason is we're looking at the fovea and the stimulus is at the fovea, so there's no need to make an eye movement at this moment in time. All right, a couple other ingredients in the model that you're seeing on the graphical user interface. The little squares here, we've got a red square or a blue square and a red square. That is the fixation node. Okay, so the fixation node receives input from the foveal region in this model. So when there's something to look at the fovea, the attention node goes above threshold and it boosts activation around the fovea and the attention field. So basically, when there's something I'm looking at, the fixation node helps stabilize fixation to that something. Just boosts activation at the fovea. There's a second node here, which is the inverted triangle. That's called the gaze change node. So the gaze change node in this model receives auditory input. So in this task, that comes from the alerting cue that says there's interesting stuff happening at the periphery. So when the gaze change node gets auditory input, it actually boosts activation in the periphery and suppresses activation around the fovea. So they kind of do an inverse effects, right? The fovea, the fixation node boosts activation around the fovea. The fixation node boosts activation at the periphery. And these two nodes are in competition with one another. Okay, so though you'll see those nodes go up and down across different simulations. And then the last element here is a reset node. So when we build a peak in the saccade motor field, that starts what's called a neural integrator, which basically tracks how strong that peak is over time and just adds up all that activation. And a peak here drives the reset node above threshold, and the reset node then suppresses basically everything. So it suppresses the attention layer, it suppresses the fixation and gaze change nodes, and it suppresses the saccade motor field. And basically the reset node is the signal to initiate the saccade. Okay, so it'll initiate an eye movement. The magnitude of the eye movement is determined by how long the peak is up in the saccade motor field and how big it is. So bigger peaks that are there longer drive bigger eye movements. Smaller peaks that are there shorter drive smaller eye movements. And the reset node, what it's doing is basically inhibiting everything during the eye movement, which is the way the brain works. So every time you move your eyes, the brain shuts down input to your eyes so that it's kind of thought to basically make sure you don't get dizzy. So if the input, if you were continuing to process visual input while you move your eyes, the whole world would be kind of smeared out all the time. So that inhibition, global inhibition, serves an important function to enable us to process the stable visual world as we sort of sequentially move our eyes around. Okay. I think I have captured all the elements there. So let's go ahead and just run the simulation. So I'm going to cheat a little bit, and we'll do this side by side. It's not really cheating, but I'm going to talk about the code a little bit so that you can learn about that stuff as I go. So in all of our code, we'll have this line if mode equals 1. So when I'm running the model in auto mode, I need to specify a bunch of stuff for that simulation. And importantly, one thing that we're always doing in auto mode is running a single iteration of the model instead of 400. Because you don't want to sit, nobody wants to sit there and watch 400 iterations of the model, right? We're just interested in watching the model once. So n repeats is 1. And then I need to specify which conditions we're going to run. And so I've set this simulator up to run all 10 conditions from the 2022 paper once. And I've set it up to simulate or use the parameters of a 10-month-old. Okay. So when I run this simulator, that's what it's going to do the first time. So let's, I'll show that by the first condition it's going to run is the valid condition. Without the C in front of the valid Q means competition. That's the condition where the fixation stays on. Okay. So let me unpause this. And what we should see first is the valid Q condition. So the fixation has appeared. The model fixates to the center of the screen. Okay, fixation goes off. Right here, there's the pre-queue or the queuing event. And we set the simulator up so the target's always on the right. Okay. With the infants, we randomize it, but the model has no memory from trial to trial to trial. So we just set it, put it always on the right because it's easier for our code. Okay, so we get our Q on the right side. So I know this is a valid condition. You could see that builds some activation in the attention layer, but it doesn't ignite a saccade. Okay. And there it actually did ignite a saccade. So that was an error trial. Actually, yeah, it was an error trial because it made an eye movement too quickly. But we'll ignore that. The next condition is going to be the invalid condition over here. So I'll keep it running. Fixates the center. Now that's the invalid Q. Starts to build activation. Hopefully doesn't ignite it does. So that made an error too. 10-month-olds make errors half the time. So this is the right setting. Double Q, we should get Qs on both sides. Yeah. So now these peaks have to duke it out. It made an error to the left on that one. And now we've got the tone. So you can see the gaze change, which is the triangle has gone above threshold because it gets that alerting cue, but there were no spatial cues. And then the target appears and it makes an eye movement to the right. So I got that one correct. And now this is the no tone. So you can see that gaze change node is not strongly activated. Target appears, makes an eye movement to the right. So now we should be into the valid condition where the fixation stays on. Yeah, so here's the cue. Fixation stays on, so there's competition. And now the target appears and it makes an eye movement to the right. This one should be the invalid condition. Fixation stays on. There's the cue. These compete. target appears, has to overwhelm the fixation, or the fixation peak, builds a peak down here, and it makes an eye movement. Now we're into the double. So there'll be 2Q, pre-Qs. Target appears. So you can see how much slower it is to make an eye movement when the fixation stays consistent, because the fixation peak has to compete with the target peak over here. So it's quite a bit slower to respond, which is what the data show. That was the no Q condition, I believe. Oh, I actually changed the order there. No, I'm looking at the wrong line. That was the tone Q, and that was the no Q. Okay. All right. So it ran through the 10 conditions. So I think Stacy had asked about changing parameters, right? And for development. One real simple way to do that with the simulator is to just say, if I come up here at the top, I've got my list of ages that this model captures. So I can just, if I want to run the 5-month-old model, right, I could just come back here to the auto or the mode 1 = 1 section and change this to a 5-month-old model. And then if I hit run, now it'll run through those 10 conditions, but with a 5-month-old. And then you can kind of get a qualitative sense of how activation dynamics for the 5-month-old work. And you can see much more noise, right? So activation's kind of crazy and all over the place. The pre-Q often builds activation, but it rarely ignites a peak down here. So the 5-month-olds are much more driven by the target, because they can't quite get the activation going from the pre-Q to generate a peak, basically. So the activation in the pre-Q period does matter, but if you remember from the data, there wasn't as dramatic of a difference between the invalid and valid conditions for the 5-month-old. And that's partly because with all this noise and with the weak interactions in neurons in the field, it just is harder for a peak to get going for the 5-month-old model. Okay, so instead of running through all those conditions, we're going to pause there. But that shows you kind of, so you can, if you want to get a sense for the differences across development in this model, one easy thing to do is to just change this from 5-month-old to 7-month-old to 10-month-old, and then you can get kind of a qualitative sense of what are the differences in how the model works over development. Now, of course, Stacy's question is really more about how do you figure out what those parameters should be for the 5-month-olds and the 7-month-olds and the 10-month-olds, and specifically, what are we changing in the model to create those different age infants, right? So let me flip down here to show you how that's implemented here in the model. Actually, it's not down here in this model, it's up here. So these, so we've got this, in this particular model, we've got this P structure, which stands for parameters. And the parameter structure has all these fields. So the dot Q size, let me actually just show you in here. And if you look in MATLAB, you can see there's this P structure. If I click on that, oh, I got to stop the simulator. Yeah, I know you didn't like that. Whoops. Sorry. Okay. So if we look at that, I just clicked on, yeah. No, that's not what I want. I click on that? Let's see, pause and debugger. Sorry, that's not what I wanted. Okay, let me try that again. So I believe the model has stopped. Yes, good. So if I go to this P structure, this is the parameter that has these 61 entries. So these are all the parameters in the model that we have to specify. Q size is like literally the size of the pre-Q in the visual, input. Fixation size is the size of the foveal input. Spatial field size, that's the size of the field. We've got these timescale parameters, blah, 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 blah. Okay, so there's a bunch of parameters in this model. If you look at the values on the right side, some of the values are just one single number, but some of the values are actually a vector of 3 numbers. And so the vector of 3 numbers are the values of that parameter for the 5-month-olds, the 7-month-olds, and the 10-month-olds. So if you just kind of scan through here, you can see, all right, this QA, that's the strength of noise in the attention layer. So that goes from 1.1 to 1 to 0.9, meaning a decrease in noise over development. Okay. This is noise in the saccade motor field, goes from 0.6 to 0.55 to 0.5. Again, a decrease in noise over development. You can see here's a parameter that has 3 values, but they're all the same. So we didn't ultimately end up changing that. You could see this one right here is, so the way to read that, C means connection strength. AA means the attention layer from the attention layer. So this is and then EXC means excite. So this is the strength of local excitation. And you can see that when we go from 5 to 7 to 10-month-olds, we make this jump. The 5-month-olds have weak excitation. 7-month-olds and 10-month-olds have stronger excitation. If we look at the inhibition, that changes across 3 steps. And the inhibition is getting stronger. So 20 to 24 to 30. Global inhibition is also increasing. You can see the value 1, 2, 3 there.
John, sorry, just to interrupt. I know you said interruptions were welcome. How do you decide on those values? What are they, just arbitrary values, or
not arbitrary at all?
Okay.
It's a great question. So how do you decide on those particular values? And you can see some of them are pretty fiddly, right? 0.0878, like, that's like really down to the like tiny values there, right?
Mm-hmm.
All right, so let's talk about how you arrive at those values. So when I look at this model, let me just to answer your question, let me do some orientation to what is contained in this, whatever, how many lines of code we have.
Yeah.
3 lines of code, isn't it? So we have 606, the devil's number, 666 lines of code. Okay. So what's in this simulation? So up front, we just have some variables to make it easier for us to work with the code and sort of specify things in English, right? Then we've got basically some details of the experiment, like how long is the queue up for? So in the experiment, we've got, and this matches the details in the actual experiment. So the queue starts 400 milliseconds into a trial. It ends 500 milliseconds into a trial. The target starts after the next 100 milliseconds. There's a 100 millisecond gap, and then the target appears. And the target is on through the end of the trial for a maximum of 2,600 milliseconds. So these numbers are all specified in milliseconds. So we set up the kind of timing in the experiment. Then we've got all our parameter values specified there, which is what I was just showing you with that P structure or parameter structure. Then here's the details when we run a full, what we call a batch of simulations. Okay, so what a batch of simulations is, we're going to save the results of the model. So these two things are true. We're going to give that simulation batch a name. And we're going to run all 10 conditions for all 3 age groups. And we're going to run 400 iterations for each of those. So we've got 10 conditions times 3 ages, that's 30, times 400 simulations. So each batch of simulations is 1,200 simulations. Okay. You could say, why are we doing that? The reason we're doing that is this model has noise. And so conceptually, we're going to, it's kind of like we're going to run 400 infants per condition. And that's not right, not quite right. It's basically, think about it as we're going to run 400 infants. So 400 5-month-olds, 400 7-month-olds, and 400 10-month-olds. Now, you could say, well, that doesn't match what you did in the experiment. Shouldn't you run the number of infants that you did in the experiment? And there are arguments for doing that. Our approach is to say, as an experimentalist, you would love to run 400 infants in your experiment because you get really robust results. You would know exactly which differences between conditions are meaningful because you had such a large sample size. Well, we can do that with a model, right? We can have a large sample size. And importantly, because the model has noise in it, we want to actually probe how that noise affects how the model works in a way that's nice and robust. And we want to know that if I see a difference in the quantitative fit as I vary a parameter, it gets a little bit better here. We want to know that that little bit of betterness is meaningful. And the only way we could do that is to run lots of simulations. It's the same thing with infants, right? If you run 10 infants in this experiment, you don't have a really good estimate of how the means are going to vary across conditions. With 20, you feel it's more reliable. With 30, you feel it's really reliable. With 50, yeah, even better. With 100, yeah, even better. And if we're trying to quantitatively match a pattern, we want a really, really good estimate of the model's behavior, and we need to run a lot of simulations to do that. Does that make sense? Now, why is it exactly 400? That actually comes from, we tried 100, and we varied parameters, and we saw that the model means were still fluctuating quite a bit. So that means we can't really say, is this parameter set better than that parameter set? So we tried 200, and we said, is this parameter set better than that parameter set? Well, it's still bopping around quite a bit in terms of the means it's producing. What about 300? When we finally got to 400, then we could robustly say, yes, this parameter setting is better than this one. We are systematically moving toward a better fit of the data. Okay, so we did that initial work to arrive at this 400 number. Okay, so that means every time, if you come up here and you set, let's say, mode to be 0, and you're going to run a batch of simulations, it'll turn the GUI off, and it'll just start running those 1,200 simulations, and it'll give you the quantitative results at the end. Okay, and including some plots if you specify that. So down here, if I go down here, you could say there's a plot latencies and plot error rates. If you set those to true, it'll spit out plots for you at the end in MATLAB. Okay. Okay, so when we're going to run a batch of simulations, we're going to run these 1,200 simulations, and I'm going to actually jump down to the end of the code and actually annoying. I'm going to open up a different simulator. Actually, maybe I'll take this opportunity to show you that there's a Python version of this simulator for those of you who might be interested. And this is the Python version of the simulator. It uses something called PyCosavina, which is basically the Python version of Cosavina. And if I just put these guys side by side, you will see that there's not a metric ton of difference here. So target size, in fact, to create the Python version, I took the MATLAB version, saved it as a Python file, and then just corrected the little code differences moving from MATLAB to Python, which are kind of minor. So like target size equals 46, I just had to delete the semicolons because Python doesn't like semicolons. So you can kind of see like line by line, there's a lot of similarity between the MATLAB and Python code. I got rid of that P structure here just to simplify the Python code. But this is basically, it looks a lot like the MATLAB code. In fact, in some ways, if you're not really a programmer, then you can spot the similarities between these Python and MATLAB pretty easily, because it kind of looks the same if you're not into the details. The point of showing you the Python code is in here at the very end. I actually calculate the root mean squared error. So, and that is, so this actually has, let me just see if it's in the, maybe I missed it in the MATLAB code. Yeah, no, I didn't. So this actually has the empirical values specified from the 2015 paper and the empirical values from the 2022 paper. And then I can quantitatively compare the numbers from the 1,200 simulations I just ran to the numbers from the empirical data and compute the accuracy, essentially, or a fit value. Okay, so that's just an example of so then your question was, how do we actually arrive at those parameter values? Mm-hmm. So we would do something like, let's say we have our hypothesis that we're going to increase excitation and inhibition over development. That's spatial precision hypothesis. So what I'm going to do then is I'm going to say, focus on these parameters in the attention field. And I'm going to increase excitation, and I'm going to increase inhibition and increase global inhibition, right? So then I'm going to first try to quantitatively simulate the 5-month-old data, let's say. And then I would try, let's say, a value of 23 for excitation for the 7-month-olds and a value of 22 for inhibition for the 7-month-olds. And I'd run my batch of simulations. I quantify how close I got to the experimental data for the 7-month-olds. And then I try changing it to 24, right? And maybe 24 and 24, and 25 and 25, and 26 and 26, 27 and 27.
Is that as time consuming as it sounds, or is there a way to like automate it to change?
Yeah, okay. So what we can do is we can actually have the model loop through all those different parameter combinations. So I can set up a loop that says, I want to explore every value from 22 to 30, increasing excitation, and every value from 20 to 30 in increasing inhibition, and every value from X to Y increasing global inhibition. And I have to make sure the number of iterations I do on the model is reasonable. We have literally set up like for loops that when we calculate it out would have taken like 18 months to run. And that's bad, of course. You don't want to set the computer running and then a year and a half later come back and find the answer, right? But we can specify all those parameter combinations. The Iowa model runs pretty quickly, like in a couple of minutes. And so I can realistically, that's what's called a grid search. So you've got all possible parameter combinations. You quantify how close you get to the empirical observations for each parameter setting. And then you find the minimum value where the error is lowest. And that would be how you do that kind of more formally. Okay? Does that make sense?
Yeah, that's great. Thank you, because I've never understood that part of it before. So that's really helpful.
Yeah.
And then I suppose you just do that for every parameter and you just go through.
Yeah. So, and that's where you have to, like, you might have to, take a strategy where you get each parameter into the right ballpark first.
Yeah.
And then you start to look at combinations of parameters to get closer to the data, those types of things.
Cool. Thank you.
Yeah. Maybe let me just kind of finish the tour of the code real briefly, and then maybe you guys will have other questions, but then I can at least pause the recording and we can take other questions. So I mentioned we've got, the task up here, task parameters up here, and then the model parameters are specified here with this structure where we've got the potential to have 3 values for the different ages in development. Then we have our kind of what we call mode control, right? How many simulations are we going to run? Do we want to plot results? Do we want to save results? That type of thing. The next section basically allows us to run lots of different parameter combinations. So I'm not even going to mention how that works, but basically this is kind of an example, like this commented line of code says, I want to vary the stimulus strength parameter across ages, and I want it to go from 50 to 250 in increments of 50. So 50, 100, 150, 200, 250. So 5 parameter steps. And then what this magical code will do that Sebastian Schneegen's created is basically pack all that into a structure that will run all those simulations kind of back to back to back to back to back. Okay, when we get down here, then we have a for loop that loops over our parameter modifications. And then here we've got a for loop that loops through the different ages. And then here we've got the for loop that loops through the different conditions. This I'll come back to in a minute. This is kind of interesting of how you specify the different conditions. So I'll come back to that in a second. And then down here, we've got the for loop that specifies the number of repetitions per condition. So that's where we're running the 400 iterations. That's like our 400 subjects. We actually, when we run this on a high performance computing platform. And what that does is, like, when you run a set of simulations on your computer at home, a lot of computers have what's called one core. And so you're running one subject at a time. Fancier computers these days might have 6 cores. And so what MATLAB allows you to do is run It's like running 6 infants simultaneously. On a high performance computing cluster, what I can do is I can run 96 infants simultaneously. So that's pretty cool, because that means if I'm trying to run 400 repetitions, right, or 400 infants, then I can run 96 in the time it takes to run one, and another 96 in another time, and another 96 the next time. And in fact, to optimize this, I would probably, instead of running 400 simulations, I would do 96 times 4, or whatever that number is. I guess that would be 396 or something like that, right? So that would then basically, it'd be like I'm running 396 infants in the time it takes me to run 4 infants. So that's a lot, basically a lot faster. So we do all our simulation work on a high performance computing cluster that allows us to basically run lots of infants simultaneously. And then down here, we've got our time loop, which is the actual, turning the fixation input on, then turning the invalid pre-Q on, then turning the target on, and then waiting for the model to make a saccade, and then that's the trial. And then doing that for the next condition and the next condition and the next condition. Okay, so that's the time loop there. And then the bottom is all just analyzing the results. So storing all the results of your gazillion simulations, making nice little plots of latencies correct and reaction times, etc. That's the same thing. Proportion correct and reaction times. Okay, let me just do one other thing, which is to come back to this section where we specify the different conditions right here. So we've got then our 10 conditions. How do we make those conditions different from the model's perspective? Okay. So what we've got here is in each row, we're specifying 4 things. We're specifying the position of where the inputs are in the input layer, the size of those inputs, and the timing of those inputs. And then input G is the auditory tone. Okay, so those are the things that vary across the different conditions. So you could say, see, in the valid Q condition, the target's going to appear at fixation, then on the right, and then on the right. Contrast that with the invalid condition. We present the target in the middle, and then the minus puts it on the left, and then the target goes on the right. In the double, we've got fixation. This is the left pre-Q, this is the right pre-Q, and then this is the target. So you can see that minus sign again. In the tone Q, we've just got a fixation Q and the target. And in the no Q, we've got just the fixation and just the target. Right, then we could say, all right, that's where things will be. How big should they be? That's the second element. So the fixation should be fixation size big. The pre-Q should be pre-Q size big. And the target should be target size big. Okay. Then what about the timing? Well, we want to turn the fixation on at the start of the simulation and turn it off after this fixation end duration. And then we're going to turn the Q on and turn it off at this time, and then turn the target on at that start time and that end time. So these are just the numbers we use to turn everything on and off. And then those vary across conditions. And then for the auditory input, there's a start time and end time for that as well. Yeah. So that basically kind of shows you these are the actual numbers we're manipulating to create all those different conditions. Okay,